So this is a work that I recently done with Juba and Edison. So this background slide here, I'm plotting the velocity. So the reddish is positive velocity, blue is negative, and brighter one is high absolute value, high value, and the dark one is like close to zero. So this is, you see this large scale vortex here. So this is pretty much the whole talk will be about. And but before I go into the talk, let me show you some curious information. So last summer, I took this trip to Lobcat. So this is one of the northernmost places in Europe. So I need to take a whole day on train to Larwick, and then I need to drive for a whole day to this place. So you can see there are a lot of nice pictures. And because the trip was so long, so I decided to take a book with me. And in this unusually nice picture of me, you can actually see which one I want to do. So my friends actually like this picture really much, and then they asked me, because they know me as a programmer, so they asked me if this is a programming book. But then I told them, no, it's actually a turbulence book, and you can tell what kind of trouble I'm in now.
The color is wrong.
It's the
The
sunset.
turbulence is supposed to be green.
Really? It's probably because of the sunset.
You can color it any way you will.
Yeah.
Turbulence comes in all colors.
Yes. So you can see that one person liked my joke. So he's actually a student here in Nordica. But I hear a few people laugh just now. So
And you're red there. You're not as red as that.
That's sunset.
yeah, but anyway, so let's go into the talk now. So this is just motivation for 2D turbulence. But since we already hear a couple of 2D talk yesterday, so I will just skip it and go to the situation. So this is pretty standard. So your U velocity, P pressure, S viscosity, and mu here is the atom friction. So that's the atom term, and F is the random forcing. And if we drop all the terms here on the right hand side, then the energy and entropy are conserved quantity. So this is pretty standard, and all we know about that. So now if we do a simulation, we put a random forcing at this wave number, then the entropy forward cascade to small scale, and energy inverse cascade to large scale. So you just based on scaling law, your forward cascade has a slope of -3, and the inverse cascade is -5. Is pretty robust feature. And just the fact that you see this thing flattening out here, you can tell this is a simulation with the atom term. So there's this large scale friction there. But so the interesting thing here is Q viscosity there is actually too troublesome. So we start to ask the question, what happens if we remove the atom term? So the standard idea is now you don't have large scale regulation, so the energy will just inverse transfer and then pile up here. And then the standard rumor is that without this regulation, then your solution will eventually go up. So now this is your, again, vorticity as the background side. And you start to see this vortex start to find each other, and then they form this vortex pair. So that's the condensate people usually talk about. Now, so now I have to mention this really nice turbulent workshop in Santa Barbara earlier this year. So there, John Bowman actually made this comment that if you remove atom friction, the system will actually saturate, but you will just take forever to saturate. And Axel was also there. So he just make a connection to dynamo theory and say, okay, so this must be the riskiest time scale. So at that time, we only did some really quick simulation, and myself was actually more interested in MHD 3D turbulence. So I didn't took that too seriously. But then after I come back, I talked to Juba, and then we think about some 2D projects. And then we start to think this is interesting because this is really a rumor. We hear people talk about it, but we couldn't find it in paper. And even in Bowman's paper, you start to see things reaching saturation, but he never really reached the saturation level. So we think it's an interesting problem to work on. Okay, so this is pretty much just the thing actually says. The time scale of saturation is the viscous time scale, and you have the energy input divided by the viscous time scale that gives you the saturation energy. Now you put this thing together, and you ask how many time steps in your simulation you need to do to reach saturation, and you finally you know that. So for a simulation with viscosity, say tension -4, then you need a billion times that. So although this is only 2D problem, it's not too clear. Numerically, it doesn't sound too challenging with billion of steps. And that's the reason we decide to use GPU instead of CPU to do this problem. So our GPU code is actually on Google Code, so you can download that. And in case you're not familiar with GPU, so this is one GPU. So it's a graphic card add to your computer. The reason people do this is if you look at numerical recipe, they actually say the computational power in the world, half of them is actually put in doing graphics. Graphics like this. And because this is computationally really intensive, so there are companies like NVIDIA, and they just make special hardware to do number crunching for this. And unlike CPU, which spend a lot of transistors doing new catching and stuff like that, all the transistors for the GPU are used for number crunching. So they are like 10 times faster than CPU. So that's the advantage of this. So now we have the setup, we have the code, and we just run the simulation.
So is this the single precision GPU or the double precision GPU?
He will come to that.
Oh, okay, fine.
What kind of acceleration do you see between the CPU and GPU on the spectral curve?
So for spectral code, I will say it's more than an order of magnitude, but then it really depends on what you compare with. So for a single GPU, we can do up to 6,000 square. So if you want to do 6,000 square on a CPU, then you probably should use a cluster. But then the communication overhead will kill you. So that if we compare that, then we get 40 times square. But if you just compare one GPU with one CPU, that's more like 10 times. And I should also say this is the latest version, so you can do double precision. Okay. So that's our simulation result, and you will finally see this condensate saturate. And depends on the viscosity, you see the saturate at different level. So that's pretty much what the actual original thing from the scaling argument. But so for each viscosity, if you force the turbulence at different scale, you actually see different saturation level. So we decide to look at this into more details. Well, actually, I should say that when the simulation was running, we were bored, so we come up with model to see this. So this is somehow a prediction. Okay, now let me show you our model. It's a pretty simple one. It's 3-scale model. So that's the energy input, the forward entropy cascade and the inverse energy cascade. So we assume the -5 and -3 slopes. And then we just say, okay, we have another energy budget that's for the condensate. So that's the model of the spectrum. Now, although this model is three scales, there are only 2 time-dependent variables because we assume this is smooth. So these are the only 2 parameters in this model.
This Ivan.
So that's the energy at the condensate. So here it should be pretty easy. Now with this model here, we can compute the energy at the condensate and also the entropy at the condensate, which is pretty trivial. And then we can compute energy, entropy, and the anisotropy. I don't know how to read that for the fluctuation. So with that, now we can go to the energy balance equation. So the evolution of energy and entropy depends on the energy inequality equation. So now we break these equations into the condensate and the turbulence, the fluctuating one. And we put in the thing we get from our model. So these are parameterized in the way that the 2 gamma, the order of magnitude dimensionless number. Actually, V2 gamma is always 0.2, this is about 1. And the k just appear to the output.
So gammas you're fitting parameters.
It is not fitting. You can derive them from the field scale model. Yeah, you assume a dissipation when you just integrate it, so you can actually derive number. And now there are three equations, and you put this in, you only have three unknowns. So that's your E, your Z, and your unit cascade. So now you have your shiny solution. And now if you compare this with the saturation timescale, that's exactly our guess. And then the saturation level is our guess with a correction pattern. And this correction pattern has this forcing wave number in it. So now if we use that solution to do the rescaling, and you can see all the solutions now are on top of each other. And I should also mention that without the free scale model, if you just use the simple scaling, then this is the scaling you get. So the free scale model, that's how you can put this on top of each other. So in this figure, there are a few curves I want to mention. So this one here, the bullish one, that is actually done by single precision. And remember, single precision, they can only do 10 to minus 7. That's the machine accuracy. And because we have so many time steps, so when you plot the energy, that you go linear with the error. So when you hit like 10 to 7 time step, you see an error that's of order of magnitude, order of units. So that's exactly what we see here. And this curve here, it looks totally reasonable, but it's actually an unresolved simulation. If you put if you do not have enough breakpoint to resolve your forward entropy cascade, then although your solution converge, they converge to the wrong answer. So it's pretty dangerous. Now, this gray curve here is actually this condition. So this really should be the prediction of our result. And you see there's overall offset. I will come to that at the end. I have to say we don't have a real explanation, but we have some pretty good idea why that happened. I will tell you the story later. Now, just the condensation level do not really describe the large scale waters. We also need the movement. So we decided to just look at the position of these waters. And now if you trace out the trajectory, say of this point, you just move with the waters. You just move these waters and you see this train. It's pretty.
For one, that's just one feature on the left. It's the trajectory of one.
So both waters actually move together.
Both.
Yeah, so it doesn't really matter. So just move and you see. But this is not too helpful. So we say if the waters move outside the box, then we just unfold the trajectory to the R square space. And this is our problem. So now it more or less looks like a random walk, except you can see it's pretty smooth. So now we want to understanding what's going on here. So we come up with another model that actually has connection with mean field theory. So we first define this mean vorticity, and mean in the sense that is only the summation of the k to the 1 mole. Okay? And now we can write down the mean field equation. That's the mean flux. So that's the average over this mean quantity. And now you put this in here, you realize because the condensate is the k equal 1 mole, the k equal 1 moles, they are the exact solution to the vorticity equation. So this term goes away, this term goes away. So you only have this. And now using this standard dynamo from here, description, you find out this coefficient actually has the meaning of velocity. And because this is just the k equal to 1 mole, and this is also k equal to 1 mole, so alpha and beta here, they must be constant in space. So they have the meaning that they are just the Lagrangian velocity of your condensate. And now we can use our three scale model again to estimate what is the velocity. The way we do that is to say, okay, this is the nonlinear term. So it contains coupling between your turbulence and also coupling between the turbulence and the condensate. And because the condensate is much higher, so the dominant term must look like this. Okay? And now this one we can just use, you go back to our three-scale model, find what is the energy in that scale, and then we have the estimate of our velocity. Okay? actually I'm hungry, so I have to go fast. I won't go to too much detail of this. I will just say, because alpha has a finite value, so instead of saying the velocity is the random variable, we say there is a defective random forcing, and then we can compute the velocity in this way, and then you do some Henry free argument in common first. And then now you can say, okay, the condensation really be an inertial Swannian motion. And then now the gray line here, there are 16 different ones. Again, the location of the vortex. And then the white line here, that's the average. And then it's a dashed line here. So that's the model. Now I should remark that the normalization here, that comes from the free-scale model. So that's a good agreement. But the fact that you turn over from an linear, from conversion to diffusion, this term over time we actually cannot predict. So that's the fitting. Okay, but we are still pretty happy with that because there's one term in. Okay, so at the beginning, in the first part of the result, I show you that there's an offset between the predicted value and the simulation, and so I promised to explain that. So now we have this free-scale model and the actual spectrum computed from the simulation, and you see on top of this open power law there's a peak here, and we start to ask, okay, well, what the hell is that? So because we can trace the movement of the condensate, we can do the opposite. We can use that to move the condensate at the middle. So now that's the condensate here. And now if I do an average over all of these things, then I can get the shape of the condensate. And that's what we get. So these are all the time-dependent things, and that's the average. And you can see the shape of this coherent structure is not just the k equal to 1 moles. It's actually something else. Okay, so now let me just say, okay, this your family function, you actually follow the symmetry of the k equal to 1 mole. So when it's positive, it's positive. When it's negative, it's negative. So let me come up with, actually that's the, so if you look at this, just take the positive part and put it as log scale, and that's what you see.
Power law?
So it's not really power law, so it's not linear.
So it's exponential.
It's like exponential, but we don't understand this. But anyway, so what I was saying is we can come up with a shape function. So that's the coherence structure. That's the k equal to 1 mole, and we just say, okay, say this is true. And if you make this, if you assume this, then f better be an odd function. Okay, because we follow this symmetry.
Yeah.
Now we can tailor expand this. So only the odd term will survive. And now you put back the condensate here. Now remember your condensate is just the Ix, Eiy. And then you take this power, and then you realize that the only term can contribute is when your Kx plus Ky are odd. Okay? And now you go back to this spectrum, and you look at the 2D representation. So these 4 points here, they are the k equal to 1 moles. So this is Kx equal to 0, Ky. Kx equal to 1, Ky equal to 0. So Kx plus Ky is odd. This one and this one, Kx plus Ky they are even, so they cannot contribute. This one, Kx, Ky is odd, so you can get energy here. And now you count this ring. So this is actually.
And that makes a minimum.
Yeah, so these two rings here, they correspond to this minimum. And this peak actually are these moles. So this, your funny shape here comes from the shape of your large scale condensate. Large scale waters. And then, and because this peak actually rise your entropy, so you will bring down your saturation energy. Well, right now we think it's too difficult to put this into the model, but I think we have some understanding of this. So my time is up. So let me just put this summary slide. So this is actually something come from Uriel's book. In turbulence, the order of thickening is important. So the standard ruler is not 1. It's just not that useful because it says you take the limit viscosity equal to 0 first, and then you take the time to 0, and then you will go up. But what we show here is we just take the limit in a different order, and then we find a more useful result. And then I also just show you the heuristic time scale, the 3-scale model, the motion, and the time harmonics.
No, the first one, it's not a limit, it's the asymptotic.
Yes.
I mean,
yeah, it's a silly way because
Non-standard analysis.
Yeah, okay. Yeah, so that's it.
Is this supposed to be some entropy maximum? It's kind of equilibrium situation, right? So the shape of this vortex must be one of this, what I would expect to be one of these entropy realizing concepts.
Maybe, but I just don't know anything. Maybe we can talk.
Because it looks like you eventually have something which is like a Brownian noise, and then dissipation is it's direct dissipation that we have just in equilibrium.
Your alpha is of course essentially a Fourier Arca effect.
Okay.
If you show that again, so maybe you could recognize it, the Arca effect.
What is that?
Anisotropic kinetic alpha effect.
Kinetic alpha.
Ah.
He did with to J. Yes. Negative viscosity. Negative turbo viscosity.
Yeah, but it's anisotropic.
But
It's anisotropic, the Arca is anisotropic.
that is a question about the name. Why is it actually, there isn't actually anything anisotropic necessarily about it? I mean, it could be well in isotropic.
I mean,
Yeah, the Arca effect doesn't have to be anisotropic.
well, I mean, then it's another effect, and I certainly don't want to claim any credit for it.
It's
In the isotropic case,
it appears in the same
with the
position.
Reynolds stresses, you just get a zero effect. Felicity doesn't help. It is essential that you have an isotropy in order to get a large-scale instability in a non-emission flow. I mean, in Navier-Stokes flow.
I mean, I think it's sufficient to have.
Otherwise, you can't get, because it all has to do with the dependence of the Reynolds pressure on the large-scale velocity, and so you need a 3 tensor there, but this 3 tensor should be can't simultaneously be the antisymmetric epsilon ij tensor and be symmetrical in I and j as required by the Reynolds stresses.
Sure.
The only
But
way
that's the
out of
case,
that
of course.
is to be anisotropic. Otherwise, I mean, we have tons of other effects, and you can dump lots of names on them.
Yeah. I mean, we have isotropy. If you are in 3D space, we have isotropy still in the xy plane. We have isotropy in the xy plane, but not with respect to the z level.
Yeah, sure.
But I think that's sufficient.
Yeah, that's no problem.
Okay, other questions, remarks? Everyone?
Just a curiosity. Do you think that the shape of your condensate depends on the way you remove the energy? I mean, if you add a small friction, you expect to see something different?
So if you add the Ekman term, then I have no idea. But I think it's independent of the viscosity. But I just think, yeah.
What do you mean? If you replace viscosity by hyperviscosity?
No, with the friction.
Otherwise, it's just partial
With friction,
No, with the friction.
with friction you don't reach the condensate.
No. Small friction, you see the condensate.
I see.
The whole idea here is that it's a system which has a viscosity acting on the scale of the box.
Yes.
Kind of, yeah.